Greetings of the day. Good evening, one and all present here. A warm welcome to the third day of Atal FTP on the topic Advanced Recurrent Neural Network for Sequential Data. It is a great pleasure to have you all here today. Once again, a hearty welcome to all. Let's begin today's session with the guest speaker, Dr. P. Ilango, Group Technical Manager, HCL Technologies, Chennai. Profile of a speaker. He qualified with PhD in machine learning from National Institute of Technology at Tiruchirappalli. He began his career as an academician and worked in various renowned institutions at Madurai Kamaraj University, Tyagaraja School of Management, VIT, and PSG iTech for 30 years. He produced 10 PhDs, and one of his scholars was awarded the best thesis for the year 2015 by CSI. He published more than 90 research papers in various international journals and 3 patents in his research area. He joined the IT industry in August 2021 and led the product development teams. We welcome Dr. P. Ilango for an expert session too. Welcome you for the session, sir.
Thank you for the introduction and the invitation to join with all of you. Am I audible?
Yes, sir.
Anybody? Okay. Right. So let me take the lead and start the discussion with the people. I thank the participants to accept me to handle one more session here on the advanced topic. In fact, 2 days back, we had a discussion on the entry level part, and we discussed about the main challenges behind taking up the input data into the RNN network and many of the issues which we are facing when we are building the models. Usually in the particular area, as I was briefing you in the earlier session, we now almost moved into deep learning. We didn't even consider the normal machine learning models because many of the applications in the business scenario needs deep learning applications only. When I say deep learning, it includes this artificial intelligence part. Along with that, only we try to automate many things. And many of the real life applications need some solutions using this AI and the deep learning models. Usually, this ML model building, a complete pipeline takes longer time to build. There are a lot of challenges. In the industrial scenario now, we don't get good people, we don't get suitable skill sets in the resource. We are unable to move forward in many of the ML based problems and automations. The reason behind this inability to identify good students and good resources for taking up the business opportunity, uh, the ability is missing to implement the ML or deep learning models in the real life environment. Hope you all of you agree. If at all you are working on this area in the research, assuming that if you are taking a problem and try to encode your own algorithm in comfortable language with your own data sets, what you are doing, if you have seen the results, and you will be definitely agree with me that we need to do a lot of development on that area. While I was attempting my own research problems, or when I am taken up the responsibility of giving the solution model to this team in HCL Tech, we need those real life problems to be automated in the practical way, and we need to see the outcome in the implementation part. Now, many issues are there. In specific, we can discuss today about challenge. One of the challenge, fixing up the threshold value when you are constructing a network. Let us again start with some fundamental flow. Then we'll get into that particular part and then try to discuss on that. You may be already familiar with the general RNN part. Here, this RNN have been used for various real life applications. The example what we have taken now is identification of the object in the real life environment. As I was referring you earlier, Mu Sigma won very good business in automating many of the airports in India and abroad. Some of the airports in India, they have installed their own ML models with the deep learning applications, and they're able to cope up with the crowd and security aspects. The main challenge here in this particular application is the success rate in terms of identifying the object, detecting the object, and how long the particular object is lying inside the airport. That means the word object or subject which I am referring here is a human being or a passenger who entered into the airport. This particular object needs to be categorized, classified after they have identified without checking any secondary data path like their own passport or their own ID proof, all these things manually, we don't have to check anything. Once the DL model has been deployed, in specific, every individual passengers need to be identified with the help of their own objects. That means their own overall picture. The continuous capturing of this pictures of various passengers getting recorded through the high resolution cameras. The moment when it is getting recorded in the streaming itself, this edge devices needs to work with this DL algorithm, try to categorize them individually first. And based on the identification, their validity authentication needs to be checked. Their Aadhaar card or their own other social security number, if it is working on the globe, these things needs to be correlated, then their identity will be verified. In no place in that particular airport, their ticket, their visa, their immigration will be checked. Once they enter into the airport, they'll directly board the aircraft. They don't have to wait anywhere in the queue for checking anything and all. They'll just move on to some circles, which is just a boundaries which we try to understand whether they have passed the level or not. If the person is not reaching out the boarding point, nowadays people are announcing the passengers to come inside or to come and report immediately. There's a final call, first call, second call, like that. Airport authorities and the aircraft operators, they are announcing and that on listening the information, the people are getting into the queue. The advantage of applying this DL model in that particular scenario, the person entered in the airport, we can easily understand. Once the person is entered, the aircraft operator people can easily wait. So these are the advantages we feel. So this particular application is a critical one which we need to focus on improving the performance and all. So in this particular slide, the actual uh, task is the classification. But before you reach up the classification, we have done various things like instance segmentation, then object detection, then semantic segmentation. Finally, it is now identified as
ఏది ఏంటి ఐడియా ఉందా? అది నమ్ముతుంది మళ్ళీ వచ్చి చేస్తాం.
request the participants to mute them. Right? So basically, these can be trained with the help of the sample data set. As I referred in the earlier session, sample data set size itself is a huge one. Training on those data set is a major challenge. We normally start with the feed-forward neural networks. Here, we use the one-step activation functions, pre-processing, then weight initialization, regularization, gradient checking. This will be done in the first step. Second part, the training issue, thus babysitting that learning process, then parameter updates, hyperparameter optimization. This is the second part of the challenge. Third will be of model ensembles, test time augmentation, transfer learning will be the third part. So wherever you take this neural network, it might be CNN, it might be ANN, or it might be RNN. And the complexity views, if it normally if you're ranking, it starts from ANN, CNN, then RNN. In these three parts, now these three major areas are the challenges. Now let us start with this one by one. This is a neural network for one-to-one activity. How do we start with the feed-forward neural network? This Vanilla is a tool which we are working. One-to-one activity, the neural network needs to start. Then afterwards, this neural network process will carry out in the next level. Then the third part will be many-to-one will be applied. Fourth part will be obviously many-to-many. You might be knowing very well this mapping cardinality is one-to-one, one-to-many, many-to-one, many-to-many is essential in terms of connecting one object to another object. Normally, the object will be connected earlier days only one-to-one and again one-to-many only. Nowadays, in all application, we try to accommodate many-to-one, hence many-to-many is possible. Think about this sequential of non-sequence data. We need to classify by taking a series of glitches. Now, there are numbers available here. How do we recognize these numbers is a challenge here. We apply a neural network here. So every segment needs to be separately taken out. Then it will be taken into the classifier. finally it should be categorized. The only outcome what we have mentioned here is number 9. The data set what they have taken in the given in the reference. So this is the basic non-sequence data function. How are we taking the data into the normal segmentation form? This is a RNN constructed. X is the input, then RNN is the process. Y is going to be the output. In the RNN alone, when you see the diagram, there will be a looping given or bypassing given. It's nothing but an output of some portion of the output has been taken and it is given to the input part. So that is referred as a looping structure. So in RNN, that is a major requirement or difference with which only we are able to connect the previous instances. We need to understand the history of the event on every occurrence. Then only we can conclude with the proper data analytic outcome. So this looping structure or recurrent structure or taking some portion of output and given into the input is so essential to contribute. Think about this. This key idea is RNN have an internal state that is updated as a sequence which is processed. You see this RNN now here. There are sets now. Not only one RNN model has been constructed. Continuously, various RNN models have been deployed with a one after another sequence. So X1 is for Y1, X2 is for Y2, X3 is for Y3, then XT is for YT. It means for every feature what you have in your system, we construct one smaller model, and within that we are processing. Output will be directly connected to the model. Think about this. We can process a sequence of vectors X by applying a recurrent formula at every timestamp. So new stat is actually derived with the help of the function fw of ht minus 1 means that h is the previously available function. That ht is the actual new state. Ht minus 1 is the previous state, old state. Then xt is the actual vector now which we are working to derive the present state. The ht is the present state. That's going to be the new state. It's going to be the prediction state, new state, forthcoming state, like that. Obviously, t minus 1 will be the previous state. So when we are moving to the next state, you know very well what is the present state. So as t minus 1 is the present state. That's referred here as a old state. As x3 is a vector which is taken from x1 to xn in terms of the features. So that xt is the actual input which will be working along with ht minus 1. Ht minus 1 will be along again working as a recurrent way, saying that t minus 2, t minus 3, t minus 4 like that. Outcome of t minus 1 is already available with us that we are working on. Then finally deriving the function ht. Think about the recurrent formula for every time step. The output will be yt, which is equivalent to f of why means h was the first step, y is the actual parameter. Then the new state would be ht. The new state what we referred here is the next stage what we are deriving out of the existing structure.
Yeah.
This is a typical network with the help of H0 to H3, refers 0 to n, then again x1 to xn. We can process the sequence of vector x by applying the recurrence formula at every timestamp. What we discussed earlier is ht is a new state, fw is the function of ht minus 1 comma xt. Xt is the present state, present vector. In every moment, this hidden vector h will be calculated. The complexity in this particular RNN is to understand the hidden part, and again, the hidden layers, how many we need to construct. In every hidden layer, what are the nuanced weights we are working on, what are the weights. This will be giving you a mathematically complex concepts. Unless we understand the Fourier series in the beginning of the part, we may not be able to construct this. So for a learning purpose, I would suggest you take a simple RNN model, try to formulate your own function, then see how the next function can be calculated. Here, the hidden part, now it is given as H. So HT has been given means that it will be from 0 to T. Right. This is a computational graph, means that H0 is the previous state, H1 is the future state, X1 is the actual current value, FW is the RNN function. So obviously, if H1 is available, now H1 will be the input for FW. Then when you are moving on to H1, your input will be X2. Obviously, you will be deriving H2. It will go on. HT will be finally calculated. That's going to be the final decision. Think about this weights and moments. The weights and moments will be the critical part here in neural network, in specific with the RNN. This weight W has been moved here or there in every location. See, the first W has been moved to FW, then again it moved to next level, like H1 to F1, then again H2 to FW, then H3 to FW, then H4 to FW, finally HT to FW, it will be deriving final outcome. This is the final outcome, what we derive. L1, L2, L3 are layers. The final completed group of layers will be a final L. So this is a next level of many to one structure. The many to one structure, we consider H0, H1, H2, H3 again. Same weight has been considered. X1, X2, X3 also considered. See the connectivity. Y will be calculated. Then Y1, Y2, Y3 will be the output. YT will be the final output. Then for every state, instead of X, what would be the value for X1, X2, X3? This is the challenge. To derive X1, X2, X3, we need to remember about the previous status and all the variables which were employed on the mathematical formula as well as the model will be used here to calculate the X1, X2, X3 values. This is now 0. It is not always 0. We'll be taking Y1 first, then move on to the values. If it is binary, 0 and 1 will be modified. If it is not binary, actual vector will be applied. This is for one to many. Earlier, what we discussed for many to one. This is for one to many. We need to produce one output sequence from single input vector here in the one to many part. Single vector part will be FW. The weight will be W2. The same, these two will be playing a role in the calculation of every state. Finally, the outcome will be derived. The character level long weight model is the typical example where we can learn this RNN model. When the word is typed, you need to predict the word possible, length, meaning, sentence in a contextual manner, connecting with all previous information. When you say hello, the next word will be sir, next word will be guy, next word will be ma'am, next word will be sir, like that it may be there. But when you type H E, automatically LLO will come. This will be calculated along with the weights of H first, then HE second, then HEL third, then HELL fourth, then finally HELL fourth. Once you type space, it should automatically support for typing or showing next possible word by formulating the same vector in a memory. That's why we need long short-term memory is required. This is a overall function, but these are all mathematically derived. We may not be able to discuss elaborately here, but once you talk, taking the information and working on your own codification problem, it may be possible for you to understand. These are all values worked on the given simple examples. The next one will be vocabulary formulation. Whatever we type in terms of sentences, the words are to be given in terms of grammatical structure. All the grammatical structures needs to be followed within the NLP algorithms. Here, at least sample characters one at a time feedback to the model. As I referred you earlier, when you type H, it will be expecting the next character. When you say E, it is expecting the next character. Automatically, the next character will be predicted and displayed. So this is the test cases, all possible combination. This is a character or language model formulating with a mathematical way, and W's are weights. This 100 are actual another combination of thresholds, and W11, W21, W31 will be the final outcome. Why are we referring here in the matrix form? We need to multiply the row with the column in terms of vectors. That's why we have used mathematical formulation. And these hidden layers will also be working with the help of row and column multiplication, finally deriving a one value. All vectors will be multiplied with the help of row and column. The final value will indicate the direction of the movement. This is the back propagation throughput time. What is the drawback of back propagation? We may not be able to predict the actual first level of origin. Numbers, what we referred here, 42 is the number of final layer in the back propagation, topmost level. Hidden layers will be again less than this 42, one by one, finally reaching the final stage. This truncation of propagation through time will be runtime forward, backward through chunks of the sequential instead of the whole sequence material. You don't have to pass all 42 in every phases. You can group it as a chunks and pass one another to store it in the long-term stored memory, move on. This is second part. This is third part. Finally, you will be writing into the one module. This is available on the GitHub. If you are interested, once it is shared with you in the group, you can check it in the GitHub to see that how the code has been written. This is a sample what they have taken for testing their RNN. If you're able to run the code which is given the GitHub, you can see the same sentences can be run on this, and the feature sentences can be produced. And if possible, if you're interested, you can remove this input set and try to feed your own input set. See what is predicting in the next level. This is train mode, train mode, train mode means the training data set is not sufficient once you start your activity. So we need to add more and more sentences. Then only we'll be able to accommodate all possible training models. That's the reason we are adding up many more sentences into this. See the things. All possible vocabulary sentences you need to formulate and give it to them. The way of writing in English, way of writing, way of passing the information from one person to another person, all will be considered in terms of this connectivity. Right. So these are all the stacks available. You can take one by one and then check it out. We were discussing about the context, taking one sentence with other sentence, predicting the next word in the given sentence. But assuming that if you are deploying this RNN for teaching one lesson to the students or to the audience, by the time how the formulas will be derived, this is a little more complex compared to that. So we need to adapt a mathematical model here to predict next level values. Then only this is possible. We are not going to discuss these things elaborately. For your reference, I'm posting to you. After the session is over, once it is shared to you, you can verify and try to learn out of this. This is a code generator after this. For this code generation and all, nowadays we have the tool. We don't have to write complete code. You can generate the code based on the semantics. This is also another code-based tool, what we are taking up. So far, what we have been discussing is only the general RNN-based executions. But here, the major challenge would be, I'll be discussing it orally, the major challenge will be taking up your own threshold when you're moving out. This threshold normally, when you apply your ensemble methods, when you are adapting entropy measures, this threshold we would have already worked on. What do you mean by threshold? Where it is applied? Just think over it. Once you construct your RNN, it is completely a internal neural network. In the internal neural network, many neurons are deployed in all the possible combination of the neurons. Every neuron will be activated from one another. Then continuously neurons are getting connected. It leads to a final decision. If you see the complexity of the network, though you have thousands of neurons, the working neurons will be only 1% out of that. So, which are all the 1% neurons working on collecting the next stage and moving on to the uh, solution? That's a question mark. And for every neuron, how do you activate it to move on to the next level? When you want to activate to move on to the next level, you're choosing the neuron, then making the neuron to work, then the output will be taken. It will be fed into the next neuron to move on. That's the actual chain reaction sequence formation working on this complexity in the formulation of neurons. Now, the threshold is nothing but like a fuzzy. If it is zero point 0.5 and above, we are considering it as 1 when you are making it rounding simple. If it is less than zero point 0.5, we are considering it as 0. Similar way, in general, the beginning of formulation of neural network, the two in the RNN, this formulation would be 1 to 1 only. Normally, it is not for many. So this formulation normally, when it is zero point 0.5 and above, it is 1. When it is zero point 0.5 or when it is below zero point 0.5, it is considered as 1. 0 means there's a simpler approach which cannot be applied to the various real life environment. So in the various real life environment, formulation of threshold is a part of ML based challenge. The formulation of threshold needs to be decided with the help of learning the previous states on the given data set, then formulating the future value for moving on to the next level. It might be 0.6 sometimes, it might be 0.3 sometimes. Not like earlier, what we said, this 0.1 is 1, or 0.5 is 1, or 0.6 is 1, 0.4 is 1, not like that. So this is the way the threshold values needs to be decided. As I'm telling it simply here, it's not so easy to formulate with the help of any observation and all. A complete mathematical model needs to be constructed. Then appropriate the sequence formation needs to be done. Finally, the values will be calculated. Next question you might be having now. In every neurons, the same threshold value needs to be applied. Some applications in the beginning, we may not be able to understand the overall pattern in the given input or training way. So in that situation, what do? We try to adapt the existing one threshold model. The same value will be worked on all the neurons available in the entire network. You might be having a doubt now when you are applying the same threshold value to all neurons, will it not have any issue? Answer is yes. There will be a bias when you are operating with the same value on every neuron formulating to the next level. So the advanced part of this neural network, or when you are deploying the neural network to the real life environment, and in turn when you are constructing your RNN specific, the threshold values cannot be changed for all neurons. Maybe for an experimental purpose, when we are constructing a small neural network, by the time this weight can be or threshold can be same for all set of neurons available in existing hidden layers. Second question, the neurons will have weights and neurons will have thresholds. Both are same or not, then all the neurons available in the hidden layer alone needs to be worked with the threshold or from input to output. Answer is we are working on only hidden layers only. The input and output will be very simple. You know very well, X will be input, Y will be output. X in the sense, set of all features, whatever available in the data set will be the input. Y will be less than the X. Y won't be always as equivalent to X. Y will be very few sets of the activities. It might be like first category animal, second category domestic animal, third category what is the animal, fourth category what is the color, fifth category what is the breed, sixth category what type of behavior. Like that you can classify. So the categorization would be given as an output with the help of your output layer after processing all hidden layers. So the weights as well as these thresholds will be manipulated, processed, monitored only during execution of the hidden layers. The challenge here is to handle the hidden layer. So how do we think about the weights? Some of the algorithms in image processing you would have heard, like threshold fixing for deciding the object is X or Y. This threshold fixing might be, as I told you, it might be from 0 to 1 if it is calculated as a first key values. When it is calculated as a first key value, you cannot decide if it is 6 and above is always good, 5 and below is always bad, or vice versa. So this value will be dynamically adjusted. Dynamically adjusted. So based on the context of the environment, these values will be analyzed and taken for decision, then move on to the next level. I was referring earlier in the beginning of the sessions, in the last day, number of neurons will be huge because we have huge size of the data set. The size of the data set, what I refer here is features. I don't refer the number of records. The setup of features will be very huge. It will be x0 to xn, xm. The m would be very huge number. Again, all x1, x2, up to xm will not be in the same nature, will not be having same boundary, will not be the same scaling, will not be in the same type of data. So the challenge here is to adapt all the information into the network with the help of its own hidden layers. Next question you might be having during our normal internal sessions, trainings, people used to ask, for every feature, do we have to keep one hidden layer? Minimum one hidden layer is required. Answer is minimum one hidden layer is required. But doesn't always confirm that one equivalent to one hidden layer. It's not like that. One hidden layer is the minimum. But if you are uncertain about the movement to the next level or based on the one feature, we need to construct some more hidden layers to conclude something out of first feature X1 or single feature X. So number of hidden layers will not be directly equivalent to the number of features what you employ. Again, people may be having another question. You are adapting dimensionality reduction techniques before you take up the data into the formulation of RNN. Once you apply dimensionality reduction technique, definitely your M will be less than that. It would be K. K will be always less than that because you are reducing some of the dimension over that. M will be reduced with the help of P sets of features which are all not required. So M minus P would be K. The K sets of features will alone be working on your recurrent neural network. So before you formulate the neural network, it is very essential to identify the set of features which are all vital to work on the classification activity. Ultimately, this neural network, this RNN, is doing only the classification work. The complexity behind this RNN is it is working continuously. It is working on the real life environment. It's not like one input is given, output is taken out, no problem, solved. It's not like that. Continuously, its streaming is going on. Recurrent network is working on. Activity is coming out as outputs. So one feature is not equivalent to one hidden layer. First take out. Second would be this setup of features are not going to be employed as itself given in the data sets, given in the real life environment. Some of the data which are taken up in the streaming but not required for your decision making process using neural network in terms of recurrent. So what do? We apply appropriate, effective machine learning based feature dimensionality reduction techniques Either it might be feature transformation, or it might be feature reduction, or it might be feature selection. Finally, the set of features which are giving optimum performance over the given dataset will alone be considered as a dataset required for constructing RNN. Only for that set of feature subset, we are constructing the neural network. In all respects, this set of features which were already selected, is it, will it be stable over the period of time? No. Today, for a given set of streaming, your system has indicated as saying that the set of features F1, F8, F10, F15, F20, F40 alone required. But tomorrow, when the situation differs, your own input streaming indicating that whatever features we have selected in the last phase of the run needs some refinement. In such situation, automatically, dynamically, your RNN network needs to identify the remaining set of features. Now, you might be having a doubt. This deep learning doesn't have to work on feature dimensionality reduction separately. You all know very well deep learning models has got some capacity of reducing the features, selecting the features effectively before it is fed into the network. That is a major advantage of using this deep learning algorithm. Whereas when you are constructing ML model, you need to formulate separate feature dimensionality reduction module, then the output will be taken into the ML model. But here in DL, it's not like that. We will be always choosing separate algorithm for DL. That algorithm in turn internally handle its own dimension, reducing it either by selecting or by transforming or by eliminating. Then the vital features alone will be taken into the process. For the vital features, your hidden layers will be formulated. Next input I would like to say is when you say vital features, this will be dynamic. It's not same. As I was referring to, as far as the data set, what we considered earlier, it might be 800 features. But maybe after a period of time, maybe 1 day or 2 day, on listening the input data, your actual input size might be varying. On working on those, your DL model will be indicating you saying that the features required for making out the output perfectly and the feature movements would be more than this. In that case, your capacity of the memory, complexity of your algorithm will get affected. So always the algorithm says that the complexity of an algorithm is fully depending on the size of the data, what you deploy. Again, I'm referring that the size of the data is only the dimension, not the number of records like that. So the size of the data when you're working on, this dimension needs to be parallelly monitored. When you are identifying this set of all features, whether it is vital or not, this threshold value will be employed there also. So first step of choosing the threshold value is required to choose whether this feature is required or not. If the feature is taken as an important feature, needs to be deployed when you are constructing a network, then that same threshold value needs to be checked first to activate the same neuron in the middle layer. Most probably it won't work. So, on that situation, whatever threshold you have already used, whatever feature you have already chosen, out of that only we need to formulate another function, then formulate the next level of threshold value. So here note the point, the threshold value what you already chosen for choosing the feature is different. And then again for the same feature, when you are constructing the entire neural network, this threshold value will be different. So the takeaway here what I'm giving you is threshold level will be completely dynamic. So it is up to the algorithm to calculate it, and your goal will be of assessing its optimization, then deciding whether the same threshold value is continuing for how much of time or these things. Such a way only the threshold part will be useful. When you are working on this threshold value will be monitored as well as processor for the next level of part. So these are all the things which I gathered in the short time just to discuss with you about the threshold part as a challenge, as advanced part of your RNN. So I thought I can stop here just talking from myself. And if all the researchers, if you have any queries with regard to this ML model building as well as deep learning model building in terms of using RNN, I am very happy to discuss with you. So please feel free to interact. With this.
Excuse me, sir.
Yeah, Rashid.
Yeah, sir.
Yeah.
Yeah, hi, sir. Actually, sir, yeah, your whole lecture was without any PPT, and so things are just floating in my mind. That's not clear. Can you again explain the term vanilla? Why we call vanilla to this RNN?
Pardon? I'm not getting it. I'm not getting it.
Yeah, sir, my question is, why we the name is recurrent neural network. Why we call it vanilla? Is
So vanilla is
any reason behind it?
vanilla is a tool like concept behind that. Being a recurrent neural network, what do we do normally? That the input is taken from the output also. It's like a feed forward. We will be taking some portion of output, then for feeding into the input part, input layers. It's not like normal taking and giving the feed forward. We use that same method for next level predictions. That way, the construction will be going on.
Okay, sir. Sir, one thing more is the RNN structure having some memory in it so that the previous output will go to the next layer and then.
Yes, I was referring to the earlier session earlier. Uh, the normal data structure models are sufficient to handle the simple ML algorithms. As far as RNN and again the simple even AN and CNN also, the memory structure is required to handle all the hidden layers. So here, one of the typical memory structure what we use LSTM. With the help of LSTM, you are able to hold the state of previous approach, previous scenario, history to decide or to contribute to the prediction of next level. We have memory structure referred as LSTM that will be used while you are constructing the RNN.
Sir, my question is, only LSTM has that memory structure or simple RNN model is having?
RNN model, if you are using the tool, nowadays we have a tool, even MATLAB also you can construct RNN. Within that tool itself, we have some sufficient memory structure. But the tool always will not be sufficient for all real life environments. In such a case, we need to adapt a separate smaller algorithm which will support for holding the previous state values for predicting the new state values.
Okay, okay, fine, sir. Sir, at the starting, you told about the object detection and segmentation also. As much as I know, for object detection, CNN is more preferable. CNN YOLO for object detection. Sir, can we do object detection using RNN models also?
Why I gave that earlier slide was to indicate you the possible application. As you rightly said, simple object detection CN would do, but this object detection will be deployed in a specific environment, real life environment. I gave an example saying that Mu Sigma has taken a real good project to identify the passengers and authenticate them to board aircraft. this will be a span of time working along with the system. The passenger may be entering in the first level entry gate after security check. From there till the end of boarding aircraft, your system will be completely capturing. So in such a case, the images captured about a specific person, where all the places he is moving around, will be very big in size. Such a case, the simple CNN model would not be sufficient. So we need to apply recurrent approaches. So RNN would be required.
Okay, sir. So that might be videos. In the video,
Yes,
when
exactly.
pictures are moving,
Yeah,
then
what we have seen is the example what I gave is if you give one image which is with a cat, you are able to identify it as a cat. This is for simple detection algorithm. But if you are working in the video streaming to decide who is moving along, whether he is authorized person, to which flight he is trying to board, where he is moving along, when he will be returning, all these things will be predicted according to these models. In such a case, the number of features will be very high. Set of all images will be very high. Though we are capturing in the video, set of all images, what we are capturing will be too high. The size will be huge. So simple
okay,
CNN would not work.
okay, fine, sir. Sir, one more question. Sir, as I am a PhD scholar, I right now I'm doing the coursework only. But I have decided to do my research in uh, speech emotion recognition, and I decided to use wave to vec. Hello,
Which started
yes, sir.
from motion recognition you said. What is that?
Speech emotion recognition.
Speech. Okay, right.
Yes, sir. Yes, sir. Earlier, my project was speech emotion recognition using MFCC for feature extraction, and I use CNN for classification. But now I decided to use wave to vec for feature extraction and uh, use CNN plus RNN in a hybrid approach for classification. So, what would you think, sir? It is
I would say
good.
your topic is directly suitable for RNN application only, not CNN. Speech and
Okay.
emotional recognition will be easily predicted and handled with the help of RNN only. CNN would not work. Maybe for the research purpose, you are taking some sample data sets and working on CNN, you may be able to construct, then see the output, identify the valuable features, take it for the decision and all, it is possible. But for RNN only, this exact speech emotional recognition will work very well. I would suggest you to focus only on RNN rather than CML. Because
Okay. Thank you,
as I
sir.
referred to in the last part of the discussion, when you are using CNN, you don't have to formulate separate feature extraction, selection, or elimination task. Whereas if you are using CNN, you need to formulate separate set of algorithms to handle the features. If you are constructing your CNN for all the set of features available there in the data set, your complexity cannot be handled by the system as well as you cannot handle, you cannot calculate the complexity also. So we will be obviously applying feature dimensionality reduction techniques. It might be selection, it might be reduction, it might be transformations. According to your real life data set, you may be applying either reduction or transformation or selection, sometimes altogether. This you have to do separately when you are choosing CNN. But when you are applying RNN, the model building might be little challenge, but this would be taken care by internal hidden layers itself. You don't have to formulate that.
Okay. Okay. So fine. So there is. I think RNN is better according to you.
But before you touch your keyboard, mathematically formulate everything, construct it. After that, you start coding. Don't do as students are entering into the lab and start coding their day by day lab exercises and all. Now being a research scholar, first formulate the problem clearly. What is the size of input? What is the nature of input? How many features are available? Then what would be the expected outcome? How do we formulate the things? Once you formulate everything, then start coding your keyboard. Till then, don't touch.
Okay, okay, sure, sir. Thank you. Thank you so much.
Sir, good evening, sir. Sir, shall we use RNN and GRU for the ECG analysis, ECG data?
ECG data, no? Yeah, time series predictions can be easily applied on RNN. Even with the
Yes,
CNN,
yes.
it's working very well. With time series prediction, you just think a little deeper. The time series mining, time series learning, time series prediction analysis can be done very easily with the help of CNN itself. But can you tell me when it won't perform well?
Sir, remembering the previous inputs for time series.
Exactly. This is a conceptual part, but if the patient health condition is being monitored continuously, when you are deploying RNN model in the same machine, his next level movement will be easily predicted, then appropriate treatment can be planned. Clear?
Okay,
So
okay, sir, please.
this RNN would be sufficient and would be more efficient also to predict his next state of the patient. Hope you might be working on medical diagnosis. You might be
Yes, sir.
developing a system to support your healthcare planning. When the patient is arriving, present condition will be monitored. When it is simple ECG, it is static image, time series. But just imagine he is under observation. During the observation period, his ECG would be continuously monitored. If he is in highly critical situation, your model will easily predict he might be getting cardiac arrest after 3 hours, after 4 hours, then he may need this medication. Like that, your health supporting system can assist. So RNN would be required for continuous monitoring, whereas ECG data alone can be worked with the CNN.
Yes, sir. Thank you, sir.
It's more interesting than just talking by myself because many of the problems we are also facing, and when we discuss, I'm also getting a little clear idea about it. So I encourage, I would be happy to discuss with you all. Please be raised your own concerns. Many of you might be research scholars, so you will have a lot of questions.
Sir, please give me your email ID so that I contact you if I will have some problem in future.
You
Please
PPT and
text.
then display it. Be useful to you instead of spelling here.
Sir, you can write in the chat box. I will copy.
Sure, that I'll do that. Right.
Thank you. Thank you so much, sir.
First one will be my office ID. If you are sending mail from your institute domain, you can send it to my office ID. It will accept. Otherwise, if you are sending it from your own personal mail ID, you can use my personal mail ID. Where are you doing your research?
Sir, I'm from Haryana, Gurugram, Haryana, Gurgaon, and I'm doing research in MET University, Gurgaon, Haryana.
Can interact with us wherever possible. Maybe I can see the scope of supporting you from HCL also.
Sure, sir. I will contact you, sir. Thank you so much, sir.
Any more discussion? Thank you. Rania, can we close the session? If there's no other please here. Okay. So let's connect to our email ID. Whenever you require any discussion, we'll discuss again to continue our learning part. So thank you so much for listening so far. What I've been discussing. Wish you all the best. Thank you very much.
Thank you for your wonderful session, sir.
Hey, Mittu.
Hello. Hello, ma'am. Sir, is it break time?
Hello, madam. Could you send feedback form, madam? link at least for this session, day 3. Madam, could you send feedback form, madam, today?
Now we have with us Dr. Gunashekaran Tangavel for today's session. Profile of the speaker. He completed his BE degree in ECE from Bharatiyar University, ME Communication Engineer from Birla Institute of Technology and Science, and PhD from Anna University, Chennai. He has 50 plus publications in reputed national and international journals and conferences, and 5 patents to his credit. He has a total of 24 years of experience and is currently working as senior lecturer in the Department of Electronics and Communication Engineering at University of Technology and Applied Sciences, Muscat, Sultanate of Oman. His research interest includes wireless channel modeling or planning, antenna design, and bioelectromagnetism. He is a professional member of ISTE, IAENG, and a senior member of IT. Welcome you for this session, sir.
Good evening, everyone. Am I audible? Yes. Satvik, am
Yes,
I
sir.
audible?
Yes, you are audible.
Sir.
Can I give permission to share my slides? Hello.
Yes, Professor, you are audible. Kindly share your.
Yes, sir.
Can you allow me to share my screen since I cannot do it here?
Kindly make it a guest as a
Yes,
host.
already I
Sir, sir, there is no restrictions for allowing you, sir.
can able to see my screen.
Yes, sir.
Good evening, everyone. Today's topic for this FTP is evaluating accuracy of output based on different statistical measures, especially in the RNN, recurrent neural networks. As we know, there is a saying, you can't manage what you don't measure. So any of the system models what we are making today, we have to keep track the model accuracy, operational efficiency, and the final impact of ensuring our model is perfect or not, at least aligned with the simulations what have been made. So with this quotes, let us start the key performance indicators, providing a set of clear metrics that can be used to track the models which we are choosing for our system approach or problem statements. So these are all the agenda for today's presentation. So I will tell you some important measures for this model evaluation and what are the metrics used for classification models, what are the metrics for regression models, and what are the loss function evaluation models we have, and what are the other constraints for providing trade-off between the training data sets and the validation of the model. Let us see the importance of evaluating the model accuracy. Why we need to evaluate the model? For example, I have designed a AI-based channel estimator. I want to study the performance of my wireless communication system with a simple 2x2 model. So here already we have conventional optimization techniques to enhance the system efficiency and the throughput of this particular channel. Sometimes in the real world problems like this, the channel is always random. So the accuracy can be misleading if we not carefully evaluate. For example, if I'm considering my channel as a frequency flat channel, or I'm considering my channel as fading channel or frequency selective fading channel. So what are the data sets I have chosen for this? The ideal data set which is available, for example, I can model this as the AWGN channel first, additive white Gaussian noise channel. Then I started to train my model with the data sets available with this AWGN. Later on, when it is coming to the practical, for certain frequency ranges, if I increase from some F1 to say F2, the transmission frequency, so I just increase, these data sets are not suited for that particular frequency. So we call it as this misleading data will always create a noisy output, or this will not drive in the adjustments or demonstrate the need of our objectives. So for this particular KPIs, how you are going to adopt the critical evaluating performance measures. Why I am telling the word critical here? The data which have been driven with these adjustments are demonstrating the overall value of the prediction. For example, the model has to provide an channel efficiency of the fading rate, say 0.3 to 0.7. If I give data set which is with a 70% of additive white Gaussian noise and 30% of the data with the other influenced data value, still we find that there will be an imbalanced data set. So we have to choose both the values equally. Then we could able to create a prediction based on the real-time data. So when we are evaluating this model accuracy, first of all, we have to measure the ability of the model to make the accurate predictions. Now, there are a lot of toolboxes available to evaluate the accuracy of our model and the prediction. And the second one, either you are in the overfitting stage or in the underfitting issue. As I already told you, either you are classifying this channel, okay, you are modeling the channel. For example, Rayleigh and Raysian are two similar channels. When I evaluate with line of sight performance, or I am excluding this line of sight performance. So only a small adjustment with this system performance will make the system to evolve enough time for confusing the operational efficiency with the end state goals. So to make this data driven decisions on the models which we have been chosen, the real-time problems and the challenges is the accuracy can be misleading. So the channel may be oriented with relay. Sometimes the channel may be oriented with the Bayesian. So care must be taken to include the specific metrics and how we are going to use them to make the most of our study based on this particular characteristics. So how do you model the quality metrics? It is very crucial for understanding the accuracy and effectiveness of the model's output. For example, you take a computation-based model metrics. The computation-based model is sometimes we are evaluating the model with some assumptions, some specific assumptions. I will tell you for the channel estimation, we used to calculate the effective cross correlation. This is one of the parameter which we assume as a scattering parameter, meaning it is having an isotropic determination of the channel models. So here, this particular decision with this effective cross correlation for isotropic model is not applicable for the directional models. Isotropic model means it will be radiating uniformly in all directions. But directional model means only in the particular direction. So my effective cross correlation have to be evaluated not with respect to S parameter estimation. We have to choose other data set which will be helping for evaluating these models. So really, are we have an ability to choose these particular models? After 2-3 years of experience, we came to know that the effective cross correlation cannot be modeled with this MIMO systems. So based on the previous experiences, either we can go with the chrono per channel or 3D sounding channel models or cluster based channel models. That's why when we are coming to this real world problems, this word accuracy have to be carefully evaluated. If it is not evaluated carefully, we cannot able to say that your model is predicting the values more accurately. So this was the general criteria which have been chosen to evaluate the prediction, regression, and loss function models. So let us take only 3 models for the today's session. One is classification model, the another one is regression model, then third one is loss function evaluation. So for example, if you take the classification model, the classification model, it will be based on the predictions which will be making in the discrete tables. For example, one of the prediction method used in this recurrent neural network is time series predictions. We know the importance of this time series forecasting, where the data analysis and predictive models are aimed to make predictions about the future values based on the historical data points in a chronological order. So in a time series, the data is collected and recorded over regular intervals of time. For example, it is hourly, daily, monthly, and yearly. For example, we have a binary or multi-class model, especially for the Alzheimer detections in the healthcare applications, the Alzheimer detections. There is one word called longitudinal parameter. So this longitudinal parameters, we have to keep a record of that particular patient, not only on hourly, daily, monthly, it is based on yearly. So these time series data includes the measurements to be very close to the models which we are taken into consideration. So the popular variants here are including this long short-term memory. We are familiar with this LSTM, or we have gated recurrent unit. So these two are the long-term dependencies, which will be helping us to build the recurrent neural network and train the model. And how we are going to evaluate the performance? That was the question. So we have a lot of limitations of this time series predictions with this RNN. So what are the advanced techniques for time series predictions we need? And what are the tools we are using to create the data? Do you have any real-time data or how you are going to generate these data. Sometimes we have a lot of publicly available data set to evaluate these type of time series patterns. Sometimes the trends, the seasonality, cyclic pattern, noise, then time series regression. These are all some of the parameters which will be helping us to pre-process the time series data. So when we are applying any prediction model, we need proper pre-processing of this particular time series data. So what are the commonly used pre-processing techniques we have? For example, you are handling the missing values. How you are going to handle it? How you are going to address the missing values and bridge the gap between the data that can affect the model's performance? So one of the technique which I mentioned here in this particular work. So we are using some techniques, either the back forward filling or interpolation technique to measure the performance of these particular predictions. Or we can do data normalization. So we can use some scaling for this dominating the model's learning time. So the learning process may be taken into the same scale. We could able to classify the particular models in such a way that which will remove the trend component from the data set. So sometimes this mislead our data set in a critical manner. So we have to choose these type of adjustments or common pre-processing techniques based on the application. There are a lot of drain validation test filter is available for the machine learning or deep learning systems. So when it comes to this classification evaluation matrices, these are all the common metrics to evaluate the classifications. One is classification model accuracy, confusion matrix, then log loss or cross entropy loss, then AUC ROC curves. Then we have precision recall, which is widely used metrics for classification problems. So when we take into consideration of these parameters, when we are really calculating these particular values for our model. For example, can I generate confusion matrix for this 2x2 MIMO to predict the channel accuracy? So this model will not be available when I'm considering the simple channel state information. So I used to generate this channel state information based on the autocorrelation functions and how this autocorrelation function is dependent at time t1, at time t2. Then I have to generate the 4 matrix parameters over here. Then how I optimally generate this 4 parameters here. So in this data set, it is very hard to determine when one is active, either here it will be 1 active or 2 active. Or your 2 is active, either it will be affecting this one at the receiver side or this 2 is affecting this 2 here. Sometimes the mutual coupling between these two will affect its own performance by calculating these values. That's why we are not supposed to take at least one measure to commonly evaluate this classification models. So we need at least 2-3 performance models at hourly, timely, or sometimes like weekly based measurements. Then those data sets have to be given as a training sets to the model. Then finally we can calculate the accuracy. So it is something like a fusion technique to evaluate the classification metrics. So in general, the accuracy is calculated in proportion to the correctly predicted instances out of all the input patterns which we have been given. So it is based on true positive, true negative, and accuracy can be misleading with the imbalanced data set. As I already told you with respect to the AWGN channel are very closely related to this Rayleigh and Ricean channel examples. And if 90% of the samples are of class 0, model will be always predicting zeros, will have 90% accuracy. But it will not be useful if I predict this additive white Gaussian noise, all the data are in line with this additive white Gaussian noise, then there is no use of it. So I have to give the balanced data set to evaluate this metric. So sometimes this accuracy may not be the correct metric to evaluate my model. So we have to go with the positive predictive values like precision. So this will give a proportion of true positive out of all predictive positive values. So this will be helpful for the spam detection. Like if the model predicts that an email is spam, how often it is actually a spam? Sometimes we send an email and we ask our friends to check in the spam. So if these type of predictions, so we can use this particular positive predictive value. But like an Alzheimer detection, as I already mentioned, so that is not possible to be checking with this particular methods. So we need a concurrent techniques, or we need something like to follow the trajectories of this Alzheimer related with the cognitive measures. So we can choose the recall where you need really the sensitivity of your performance. Now, when we consider the measurement of a 3D channel model in relation with the cluster type, in clustering, what we are doing, we are taking the past values as one of the major input value. Then we will feedback those past values from the memory, and it will be correlated with the functions which are given to the current data set. So there will be a strong recalling parameter. Then when it will be given to that particular parameter, for example, if I'm choosing this recall for my channel estimation, so 90% of the time, the channel will be always aligned with the true positives, but it is not matching with the actual positives. So I cannot always believe the sensitivity or the recall method will help me to find the suitable accuracy model. So when we move with this false negatives, which are always costly, meaning we have to sacrifice the time, training data, as well as the model accuracy. So that we have to be careful to choose these type of evaluation metrics to the models which we are taken into considering. The next one is the F1 score. This is one of the balanced precision. So this score, we know according to the formula, the precision into recall. Again, you have to go with the previous model. And when it is dealing with the imbalanced classes, this cannot be a suitable measure for analyzing the numerical values. So if the data set is always aligned with the n number of numerals with the absolute error, then this particular parameter may lead to calculate the measures which will be characterized by the temporal trajectories. So what do you need again here for recalling? So you need some status which is using from data of the n number of participants or n number of studies. Then we have to further progress these values with respect to the F1 score. So for example, when you are examining the longitudinal progression of your medical data, here the data-driven method is important for evaluating the earlier indicators of the disease. So we need both of our parameters to be closely related with this longitudinal trajectories. Therefore, we need to choose the more appropriate selection of these measures and based on the clinical trials. So that's why we used to say that if you want to ensure both precision and recall, that should be good enough to model the methods which we are proposing. So especially when we are choosing the cognitive results, or when you are going away from this channel matrices or your trajectory studies in the Alzheimer diseases, we need to calculate this score as a progressive manner. So despite of this versatility, we have to be in a position to characterize this longitudinal changes for the measurement. So this is the other category. The next one, which will be involving with respect to the area under the ROC curve. We know when we are using this, this score is a single number. We know that, which summarizes the classifier's performance. And you know, this type of characteristics curve, area under the curve, what should be the score? Either the score between 0.5 to 1. If it is 0.5, there is no discrimination. If it is 1, it is the perfect classifier. So what could be the optimum value we can choose based on the rate between true positive versus the false positive? So usually there is no exact values of acceptable conditions given over this receiver operating characteristics. So what is this curve to tell us? It is used to give a assessment for the overall diagnostic performance of the test. And it is used to compare the performance of 2 or more diagnostic tests. So this model will be ability to provide an AUC of around 0.7 to 0.9. For example, if your AUC is the ROC score is, for example, 0.8, it means that 80% of the time the model will assign a higher probability to a positive value rather than the negative one. Okay, so like this, we can choose the score to develop your model and test your accuracy. And we have a question. Is it give a better than AUC is better than the accuracy? So we may ask a question. Almost it is similar to the binary classification problems, especially with imbalanced data set. The threshold which we are fixing over that particular value is similar to that of the accuracy what we are giving to the matter of some 30 to 40% of the original data set, which is the relevant prediction models during the training time. So this particular AUC is sometimes better than the accuracy, not always. Sometimes it is better than the accuracy, meaning which considers the performance across all positive classification thresholds rather than a single threshold like your accuracy. That's why this may be the suitable metrics used to classify your models in the beginning stage. But we can't believe this one alone, but we can able to interpret these AUC values based upon your diagnostic patterns, especially for the medical images and medical data sets. The next one is the confusion matrix. Very interestingly, this confusion matrix will give a specific problem of statistical classification. So this confusion matrix, sometimes called as error matrix, we know that this specific table is showing here how this particular confusion matrix is helping us to visualize the performance across multiple classes and types of error. So these type of confusion matrix always represents the prediction summary in the matrix form. I hope you remember here, as I told you, when we are calculating the channel models with respect to 1 to 1, 1 to 2, 2 to 1, 2 to 2, or between these 1 to 2. So if you choose this particular values based on the matrix performances, and it will be very easy to predict how many are correct and how many are incorrect per class. For example, at time T1, my 1 will be active, 2 will be inactive in the channel model. So I can able to choose these 4 values with respect to the confusion matrix. But you know, there are 2 errors here. One is type 1 error and another one is type 2 error. We all know when we are rejecting this particular null hypothesis, it leads to fail the prediction of the first value in comparison with the statistical significance difference between the false positive and the false negative. So we cannot able to say that 1 and 2 itself is mixing each other instead of relating with respect to the covariance parameters. So that this particular model can be applicable for the medical diagnosis, especially with this MIMO models, massive MIMO models. So here we can able to use the objectives of this confusion matrix and which helps the classification model performance in machine learning by comparing the predicted values against the actual values for the trained data set. These are all some of the regression evaluation metrics. In the regression, we are using mean squared error, root mean squared error, mean absolute error. So these are all the metrics which are all evaluating continuous predictions. Let us take this mean absolute error. So the average of this absolute errors between predicted and actual values are defined as the mean absolute error. See, only these two statistical measures, one is the mean, another one is the variance. So how we are going to observe this mean for n number of samples you are considering, and how you are going to take the variance. Usually this variance, we used to say that it is the noisy data set and the mean will be the required one. So we have to maximize the mean, minimize the variance. So this is very simple and interpretable. This is the way we used to interpret this particular data in relation with this particular values. So when we calculate this mean absolute error for the collected data set, what are the possible values of moving from this mean absolute error to root mean square error? Both looks like same. So which is better? Either we are going for mean square error or the mean absolute error. So there are two significant objectives we have to take into consideration. For example, what model you are considering and what are the type of data you are adequately chosen for the training and what is your objective. So if the data has outliers or noisy, then your mean absolute error might be more reliable than MSE. If the data set has long variant, okay, either in relation with the time or in relation with the other higher parameters, your mean square error will be the appropriate parameter. So wherever variability is more, we can go with the mean square error. So is this mean square error and mean absolute error are covariantly applicable for all the models? For example, I have to classify my channel from Rayleigh to Raysian or Raysian to Rayleigh, or it will be an indoor channel, for example. So how effectively I can change my model? For example, I am using a modem in my home. That Wi-Fi modem is operating in two different frequencies. One is 4G, another one is 5G. If I want to shift the model, if I want to change my modem is always representing with respect to these two different frequencies. If I want to select the 4G, that is 2.4 gigahertz, my mobile has to consider not considering the surrounding obstacle. Since my channel is very direct and these frequencies are not prone to that much noisy environment. When I choose the 5G frequencies are more prone to path loss. So where we have to calculate the mean square error based on the blockages or based on the obstacles in a room or in a closed environment. So we have to choose those data set and we have to consider the correlation matrix between the equipment available at location 1 to the receiver available at location 3. So like that, we have to include the n number of scatterers inside the mean square error. Then you can able to calculate this particular parameter. Imagine I have 20, 30 obstacles in the room. So my error will be more. When large errors are available, this mean square error calculation becomes more critical. So then what we have to do, again, we have to go with this mean absolute error to calculate the values. But here, the predicted value and the actual values are having a significant improvement with respect to the data set. So that care must be taken to choose these two parameters in the model. The next one is the root mean square error. So this is the one of the commonly used values. The advantage of this one is it will allow us to set the target variables. If I have 20 scatterers, I can set around the one which is more closer to my transmitter are the strongest variables which will be taken into consideration. So when you need interpretable error, then we can go with this same scale with respect to the root mean square error. So what is the relation between these two? How we are going to interpret this root mean square error? So this model will, this particular metric will give the model's predictions reliably. Meaning, if the high root mean square value implies that there will be a poor performance in the network. However, this root mean square error is high or low. It depends on the context and the problem domain. I will give you two examples here. When you take an outdoor reliability with respect to this cell phone tower, okay, then this tower has to correlate with n number of users. This is the model which I'm going to train my system, okay, and I'm considering, for example, n number of users, okay. Then I'm switching the beam from 1 to 2, 2 to 3, 3 to 4, and etc. n to n minus 1 to n. So these many number of trials I could able to make. For example, I'm considering 500 users, user data. Then I'm correlating this one cell phone tower with respect to the noisy environment available with this particular channel. And I'm considering the first equipment is a television. The second equipment is your tab. The third equipment is your mobile. So, yes, please.
Hello.
Yes, please.
Sir, firstly, you told about the this
Yes, please.
metrics, the precision recall and F1 score were the metrics. And
Yes.
now you are telling about the errors.
Yes, ma'am.
Sir, according to my knowledge, I think metrics will be same for all CNN, RNN, and the machine learning methods. Am I
Yes,
right,
yes,
sir?
yes, yes, you're right. I'm
Ah,
taking about the particular problem, and I am sometimes this misleading towards this. That's why I'm telling you.
okay, fine, sir. And sir, why are you telling these errors? How they are related to RNN? Please explain it also.
Yes, ma'am. Why I am choosing these things to be related with this RNN? These are all the conventional method of evaluating your models. Will it be suitable for RNN? That was the question. That was the final aim of this particular presentation. Will it be suitable for evaluating your models with respect to the interpretations what we have been done with this test sets?
Okay, if I will find the errors, so is it related to the loss which we need to calculate in the RNN, or it is something different, sir?
It is depends on your application, madam. Which one you are focusing? You are focusing on noise or you are focusing on the actual values?
Okay.
You got it, madam?
Yeah, I'm trying. Thank you,
Yes,
sir.
ma'am. Actually, I have two values here. One is for predicting the different data sets. For example, the users are not common in my example. The TV, the mobile phone, your, what you can say, the gadgets like a tab. So everyone has its own classification. So either I'm using only TV or I am considering only all the mobile phones for prediction of this channel. That was the question here out of this 500 users. So what could be your error? Is it will be the targeted value or the interpreted value on the same scale? That is the question. Yes.
Okay, sir.
So we are targeting towards the absolute and relative error based on the applications what we are choosing. Okay. In which area you are working, ma'am? For this one, either it is a machine learning model or it is some other model, ma'am.
No, I was just asking to whom I relate these whatever you are telling.
Okay. So actually the problem is here, these two values are related with respect to 0 to infinity. Where we could stop, that is the question, madam. I'm indirectly saying that. So either all are negatively oriented score, your lower values are better. Are you able to follow me, ma'am?
Yes, sir.
Okay. The next one is the R square. So this is the proportion of the variance in the dependent variable that is predictable from the independent variables. This is one of the parameter which will be closer to 1, means better model to fit. This is commonly used in regression analysis. At the end, I will show you some of the CO2 predictions based on this regression analysis, how this R square error is to be calculated for different models. The next one is the adjusted R square. For the adjusted R square, the number of predictions in the model will helps to compare the different number of predictors. For example, if you have n number of observations in the data point, then p number of predictors as independent variable. Then the adjusted R square is equal to 1 minus the R squared of the model into the number of observation minus 1 divided by n minus p minus 1. This is the adjusted R square for. This is one of the example for adjusted R square. Consider the scenario, we have data set with 30 observations and we create a multiple linear regression model with 5 predictors. Then based on this example, they discover that this R square error is 0.8. Then let us calculate the adjusted R square based on this value for 30 observations, and it will be given as 1 minus 0.8 and 30 minus 1, like, then it will be the adjusted R square is equal to 0.7. So what does it imply? This adjusted R square. Are you happy with this 0.758? Or do you need a model-based predictions at this particular stage to calculate the parameters based on the accuracy and the effectiveness of your calculations? So these things will be based on a general models which will be helping us to analyze and highly effective for regressions. The next one is cross entropy loss in RNN. This is the preferred loss function for classification task, especially when the output is usually categorized. So this cross entropy measures the dissimilarities between the true distribution and the predicted distribution. For example, I have a predicted value of y less than or equal to, for example, n. This n may be 0 or n may be 1. So this y value, how we are going to choose? So the negative summation of over all possible values that random variable can take. So the product of the true probability and the logarithmic value of the predicted probability taken into consideration. Always the logarithmic scale used to compress the value. For example, I'm giving you a simple model. When you take log 10, 10, finally it will become 1. So this cross entropy loss is a downscaling problem. So it will help us to maximize the probability of the correct class. So these type of losses can be taken into consideration, and the true output has specifically pertains to this class. So we have a 0 probability mass. So the value is product of true probability. Essentially, only one term remains the summation, and the term corresponds to the true class as the entire probability mass of one in true distribution. So this will be one of the parameter which may be taken into consideration to leverage the strength of the model, and you can choose this one based on the models which we have applied for the applications. The next other considerations in the model evaluation, we have cross validation using different data spills to assess model performance, traditional cross validation method or time series cross validation method, and the bias variance trade-off balancing model complexity, which will be based on the avoiding overfitting or underfitting. There are two methods: U-shaped test error curve and bias variance trade-off in linear regression. Then hyperparameter tuning, optimizing model parameters for better performance. Either we can go with the hyperparameter tuning for your neural network. There are separate parameters for SVMs and XGBoost. The hyperparameter optimization techniques, there are many techniques available to evaluate the model, but based on the medical classifications and medical application determination, like you are categorizing text in predetermined sentiment classes, encompassing positive, negative, neutral, and occasionally very positive, like so many optimization models you can consider. The conventional optimization models always yields to provide a lower performance metrics in terms of classification accuracy. Therefore, we need a more sophisticated and a clarity approach for this particular applications. So let us take one practical example for evaluating spam detection model. So based on this particular thing, you can see the analysis stage. We are removing the undefined values and converting all letters to lowercase, tokenization, counter vectorizer. Then next is the train stage. So here the conventional logistic regression decision tree random forest, anyone can be chosen accordingly. Then the test stage, look at this. What are the measures they have been considered? Accuracy, precision, recall, F1 score measure, ROC area. So like that, in the test stage, here they have to go with all the measures. So how much time we have to wait for to classify your email is spam or not, that doesn't matter. Imagine an MRI image is given to you and we have to evaluate the deduction with the classification matrix. Will you give enough time to the technologist with the doctor for this particular classification model? For example, you are taking the same patient's longitudinal graph and the longitudinal details for more than 2-3 years for this particular deduction. So we need a certain integration of this models with this RNN, where this enhanced accuracy will be coming when you combine the contextual embeddings with this RNN sequential modelings. That's why I told you which will be improving the classification accuracy in a better way. So this is evaluating the price prediction model. This is with respect to the actual value based on the mean square error, root mean square error, R square error, like that. And what are the tools and libraries we can follow? These are all the general libraries and tools we can evaluate with respect to this metric calculation. We are using this MATLAB for specific application areas. Since our areas are mostly with the dynamic system modeling for estimating the channels and the predictions of data set for MIMO antennas. So we have been choosing this particular application based on the analysis which is available in the models. So one of the model which we have been using here is ARIMA. This includes both time series forecasting and hypothesis testing for estimating the multiplicative and ARIMA model. And these are all other applications for condition monitoring and predictive maintenance, signal analysis, and for deep learning. So sometimes this particular MATLAB toolboxes allows some external interfaces to the system. So that can be used to combine with the cross compilers. Nowadays, it is allowed to work with your LabVIEW also. So you can able to develop a model with the real-time data what you are generating, and you can give it to the system with the extract regions of interest from the data. So let us see the evaluating sequence predictions, the specific challenges of sequence prediction tasks, then evaluation using sequence specific metrics, then examples of sequence predictions versus true values. Let us see this case study 1, which is a text classification case study. In this text classification, you could see they are generating integration of this PET and RNN together. And they are calculating accuracy versus F1 score in the imbalanced data set. The steps are data pre-processing, model evaluation, and metric selection. So here, the text classification model is very simplest model, and they can use this multi-gate attention with this linear predictions and the PERT. So when you are combining these two models, what are the classification? What are the classifiers which you are going to encounter along the models with the classification data? For example, when you have a stock price prediction using this RNN, so how you are going to use this RNN network to predict a particular stock in terms of its value cannot be applied to this particular close prediction accuracies with this text classifications. So if I choose this particular model for evaluating my MIMO for the same technique, which we are, as in the beginning stage, we were in a confusion to choose these models to analyze the channel for the text classification. So this is very difficult for us to calculate the matrices which are required to evaluate the model with respect to the eigenvalues. So we have only the isotropic parameters, but here this one needs a more directional way of moving from 1 to 2, 2 to 3, like a sequential variances. So that this particular model cannot be suitable for our work, so that we have been combining this work with the time series predictions for the real-time applications. Here, the matrices are RMSE, root mean square value, and MFE for the stock price prediction application, which is applied in this paper. These are all some of the advanced evaluation metrics for RNN. So this Matthews correlation coefficient, log loss coefficients, these are all some of the matrices which are available over F1 score and accuracy in binary classification evaluations. So basically, if you want to evaluate the binary classifications, and we need their confusion matrices, and we need crucial issues like what are the accuracy and F1 score you are computing on this particular value. So we have to be taken into considerations with this effects. So this Matthews correlation coefficient will be a more reliable statistical rate, which produces a high score only if the prediction obtained in the good results. So with this 4 confusion matrix categories, so this Matthews correlation coefficient may be proportionately varying with respect to the size of the positive elements and size of the negative elements in the data set. So most of the researchers in terms of the clinical feature data set, they are using this MCC instead of measuring the accuracy F1 score for evaluating the binary classifications. Then one of the method in the accuracy with respect to MCC and F1 score, the most reasonable performance metrics is the ratio between the number of correctly classified samples. So how you are going to evaluate the number of samples in one class is much larger than the number of samples in the other classes. So accuracy cannot be considered a reliable measure anymore. That's why an effective solution for such a type of cases, this MCC will be allowing us to correlate this number of matrices defined in terms of classification, and how you are going to develop this MCC. That is another method of identifying the constants which we are the assumptions which we are making with the classification data sets and the classifiers. These are all some of the hyperparameter tuning and evaluation matrices. So here, the hyperparameter tuning processes, they're using the metrics like grid, random, Bayesian. So these are all strong probabilistic approaches for calculating the accuracy. Then the same thing will be given to the feedback with the optimization algorithms. Either you can use the genetic algorithm or PSO or your quantum optimization techniques. based on your problem type and the validation model which you are choosing. So this hyperparameter tuning may help you to impact on your evaluation in a macro level to that micro level to macro level. This is one of the comparative study based on emission forecasting in the Gulf countries using auto-recursive integrated moving average artificial neural network, Hall-Winters exponential smoothing models. Based on different years, like starting from 2015 to 2025, they have been evaluating different parameters in the areas like Kingdom of Saudi Arabia to Oman, and they are measuring the metrics like the prediction of the CO2 emissions, and we are calculating with respect to the performances with this ANN models instead of the normal or the conventional models. They are using this Hall-Winter exponential smoothing model will give you a better accuracy than the conventional artificial neural networks. So these are all some of the best predicted value of CO2 emissions for the year 2025. And this was closely observed with this model will provide accurate measures with respect to the data available for the previous data sets and the corresponding values which will be given to the models. This is the novel hybrid machine learning model for prediction of CO2 using socioeconomic and energy attribute for climate change monitoring and mitigation policies. So here our models, this RNN can be helpful instead of this particular conventional type. So hybrid models and deep learning models like your RNN, LSTM, TabNet may help us for the linearly predicting these things to be attained at the levels. So this is another case study with vehicular CO2 emission forecasting using time series analysis. So these are all some of the challenges in evaluating the RNNs. So these are all self-explanatory, starting with overfitting and underfitting issue, data sparsity and missing values, sequence length and fading effects on evaluation. So what are the practice tools available for this one? So we can use the scikit-learn, TensorFlow, Keras or PyTorch. There are a lot of models available even with this Python and MATLAB can be combined together. You can use Simulink models to create your conventional neural networks to be converted with this particular LSTM, or you can go with the supervised models with the machine learning techniques, and you can calculate the key functions and evaluate the cross-validation functions. So these are all some of the examples for performing validation for time series with MATLAB. So once we create a model and we train the model and we got the correct output or not, that could be based on the measurement what we are going to make with the performance study and characterization parameters to be taken into consideration. So not only for RNN, for any output accuracy is multifaceted and it should be calculated with respect to the data on the hand. So in line with our experience for channel measurements and channel modeling, the conventional optimization techniques may not be the suitable one. So we go with this artificial neural networks and we used a 3-step models with respect to the error matrix and the channel models, which will be applicable towards the measures like cross entropy loss, F1 score, or the metrics like MSC, which are all the suitable parameters for models which will be providing well-suited training sets with the given frequencies and the data set. So in conclusion, choosing the right metrics is vital for assessing the network RNNs or any ANN's performance and understanding its predictive capabilities. So it is essential to evaluate not only accuracy, but also metrics that highlight the strength and weakness of the model in different contexts, leading to more informed decisions on model optimization and deployment. These are all some of the references. Thank you so much for your patient listening. Thank you, everyone. If you have any queries, please you can. Yes, if you have any queries, you can. Yes.
Can you please explain the accuracy of RNN, sir?
Hello.
Sir, can you please explain the RNN, sir?
Didn't get you.
Sir, can you please explain the accuracy of RNN?
Oh, that is the accuracy parameter. You want to. Hello. Actually, the accuracy is based on the performance which we are taken into consideration for RNN. Okay. So it will be either based on the predictions with the true positive and true negative values. So the accuracy is the parameter which will be giving based on the model training, which starts from a value which is minimum which you are fixing with your model. For example, if you take a LSTM model, the training accuracy will starts at a value of around 98 or 99.5 or 0.3, and it may be go up to 99.99. So if you take the GRU model training, the accuracy has to start lesser than those values, and it will be reaching at 99.99. In general, any neural network, this accuracy will be calculated in terms of the coefficient of determination and the reliable prediction capabilities. So based on your model, so you can able to train with 75% of the data and tested against 25% of the data. The error in computations are based on the testing data. So this will be one of the metrics to evaluate the accuracy of your models. Okay, sir. For example, if you have some score like 80%, that is 0.8, your.
Thank you, sir.
Hello,
Yes, please.
sir.
Yes, please.
Sir, can you add this?
Yes, ma'am, please.
Sir, once again explain RMSE, sir.
Mean square error.
Yes, sir.
So this is based on the over data of RNN trained over the other values. So for example, when you have an autocorrelation matrix, for example, with respect to my model in the 4x4 or 16x16 MIMOs, we are calculating the eigenvalues based on this root mean square error. So when I am evaluating the eigenvalue parameter in correlation with this 4 antennas at the transmitter end and the 4 antennas at the receiver end. So I have a 16 element matrix. So I'm going to calculate the difference of this particular RMS values, and I am calculating the exact value which match precisely with this expected value. For example, if my model is having a discrete motion of predictions, for example, I have antenna 1, antenna 2, antenna 3, antenna 4 at the same time, but the convolution which have been taken into account for calculating the probability at time t1 is 1 to 1, 2 to 1, 2 to 3, like a discrete value, then the prediction performance is not feasible with this root mean square error. So if I am leaving this conventional method, if I am going towards this AI models, the performance measure should be in continuous motion of prediction instead of considering this, which will avoid the average differences of these actual points and the predicted points. That's why these AI models are always better for evaluating the performance of the channel matrices in terms of high frequency and high noisy environment rather than the conventional root mean square errors. That's why a clarity must be there to explain the model's variability in terms of these errors will provide a suitable measure of independent variables in the models. So shall we have this values greater than 2 or greater than 4, greater than 1 like? Obviously, this will be depends upon your outcome. That is the variable which we are using at the models. For example, if I'm using an 4x4 MIMO, my prediction RMS value may go up to some 25 to 45 based on my Rayleigh channel or ICN channel. If I consider an additive wide Gaussian noise channel, this RMSE will be depends upon the temperature which is affected with the transmitter and receiver in the channel. So based on my specific characterization parameters, we can able to calculate this RMSE, and obviously it may be greater than 1 and it may be sometimes not possible to accurately calculate. That's why we are expecting these values for normalization with respect to 0 to 1 will give you a graphical representation easily to be fit into the curve. That's why this R square value, we are always going to be putting into a normalized curve value from 0 to 1. So based on your model, you can able to take the parameter and you can measure the uncertainty.
Excuse me, sir.
Yes, please.
Sir, what I get from for evaluation metrics like accuracy F1 score and precision recall, or are evaluation metrics that we do at the end of our training them after doing the training model when we are evaluating the model, right?
Yes, ma'am. Obviously.
Sir, but I didn't get when to find the errors which you mentioned, na, when to find it. Kindly tell me in a layman language. As much as I
Sure.
am getting, sir, as you said, 0 to 1, find the value 0 to infinity,
Yes, ma'am.
which I am getting, that is the threshold value. When
Yes, yes.
we find the activation function, then we check the threshold value. So I am getting confused. Please clear, sir, in totally a layman language, sir.
Okay, ma'am. Ma'am, actually, when I am speaking about the general conventional models, instead of going towards this neural network or RNN or whatever it may be, you just calculate the root mean square value. According to mathematical formula, it is simply a standard deviation, right? Based on the values what you are getting, and then based on the output, you are calculating the standard deviation, right? That is the actual
When to calculate this? I mean, if I input layer, hidden layer, output layer, what is the time to calculate it when I am training a model?
Yes, ma'am. In each level, ma'am, for example, you are at the output stage. For example, you have come across all the training finished, and you have time T1. You have an output. So, for example, you have a set of output taken into that particular data. Okay.
Okay.
Then when you are calculating these matrices, you are going to evaluate the whole model, not the individual performance of each layer. If you can apply this particular thing to your individual layers also, but the system which we are talking about is the entire output, evaluating the performance of the model, not the layers like independently. That is based on, you can go with some optimization models which are all allowing you to check stage by stage. Even in MATLAB, you can.
Fine, sir. I got it. I got it.
Yes, ma'am.
Fine, I got it.
Okay, ma'am.
Okay.
Thank you for the valuable session, sir.
Thank you, sir.
Dear participants, kindly fill the attendance and feedback form for session 2 without file. It was posted on chat box.
Sure, sir.
Thank you so much for the patient listening and have a nice day. Okay, see you all. All the best. See you.
Thank you. Stay tuned. We will meet tomorrow.
Mhm.